Okay, PS4 is due today and tomorrow. Any questions about it? Any problems? Yes?
Yeah, can adjacency list be power performance of E times V at all?
Say that again.
Can adjacency list have the performance of E times V at all? EV?
So an adjacent, what operation on an adjacent
In
list?
general, I was wondering if it could get to that case.
Well, in the worst case, so he's asking, could there be an operation of complexity E times V on adjacency list? Well, if it's a complicated operation, yeah, but the thing about it is, in the worst case, E can be V squared, and should be so you're talking about a V cubed algorithm. And, you know, it would have to be an operation that you did, say, V times or V squared times to get that out.
Maybe some of all edges, but it would only work in list form and not matrix.
Yeah, if you get it, you're talking about a JC list?
Yeah.
If the JCC list and you wanted to sum all the edges up, it's just, what would it be? If you just want to basically traverse the structure and add up all the edges, all the weights.
This is V plus E.
Yeah, V plus E. You have to consume the entire structure. You just have to walk the whole structure. Anytime you have to do something to the entire structure, that's E plus V. Anything else? Okay. We get lots of questions about the Caddis problem, so I want to talk about that, even though no one wanted to ask a question about it. So the Caddis problem, in case you don't remember, is since you got a graph of cities, and it's a DAG, so there's some kind of one-way streets between certain pairs of cities, but no cycles. Why is it called autosync? Why did I name it that? Yeah. Yeah, all the cars will end up in the sinks because they can't drive back where they came from. So the idea is there's a toll for entering each city. So maybe the toll to go into this city is 2, and the toll to get in this city is 4, and so on. And you've got some start city, maybe number 2 here is your start city, and some destination city, maybe that's this one here at the end. And you want to find the minimum amount of tolls you must pay to get from, in this case, city 2 to city 1. In that case, it would be, you'd have to pay 6 to get into this city right there. And then, I didn't put a toll. Okay. What would you do next? No, not very interesting. We'd go up to 4 and down to 1, so the cost would be 11. If I put in a road right there, it would be 6 plus 3 plus 1, which would be 10. That would be the least expensive. So that's the setup for it. Any questions about the setup? Okay, so let's put that example aside and just think about the problem in the abstract. There are a bunch of vertices, but there are only a few different kinds of vertices of interest. So one is the destination city. So this is the destination. And it may have some edges out, and it may have some edges in. We don't know. It could be a source, it could be a sink, it could be somewhere in the middle. Now, what I'd encourage you to do was to come up with a way of associating with each city the cost of getting from that city to the destination. So let's call that cost of X is going to be the cost of getting from X to the destination. And if you can associate that cost with every city, eventually you'll associate that cost with the start city, and that solves the problem. Okay, so suppose that that's your what is the cost of the destination? What is the cost of getting from the destination to the destination going to be? In other words, you start in the destination and you want to go to the destination. Zero. Right? So that's one kind of city. The cost to get to the destination is zero. So that's easy to compute. You can do that first. Imagine you're filling in a hash map that maps each city to the cost of getting there. Each city to the cost of getting to the destination from that city. So cost of destination will map to zero. Now, you'll have some vertices that are sinks. Now, assume the destination can be a sink, but we've already dealt with the destination. Suppose you have a sink that's not the destination. So there are edges in, but no edges out. What's the cost of, let's call this vertex U here. If U is a sink, what's the cost of getting from that sink to the destination? Again, assuming that the sink is not itself the destination. It's not possible, right? If it's a sink, there's no way out, so there's no way to get to the destination. So let's just treat that as infinity. Okay? Now, I'm just, as an aside, you may be tempted, let's say, programming in Java or C# or C or whatever, to let infinity be represented by the maximum integer. Well, there's a gotcha lurking there where if you add anything to that maximum integer, you're going to get a negative integer. So just keep that in mind, that when you're computing things, that you gotta deal with this infinity especially. Now, another strategy, instead of making it the maximum integer, is the problem tells you what the maximum total is, and it tells you what the maximum number of vertices are. So that gives you an upper bound on what a real total could be. So anything bigger than that is fine as infinity. All right, so we've solved two special cases. We know the cost of a destination. The cost of the destination is zero. The cost for any sink other than possibly the destination is infinity. So all that's left is sort of a picture. Let me. Other vertices U. I'll call them V. So other vertices V. The picture's going to look like this. There'll be maybe some edges in, maybe some edges out. Okay, there'll at least be edges out, and maybe some edges in. So we don't know if there are any edges in, but we do know there are edges out, otherwise it'd be a sink. Okay? And these edges will go to some cities. What's the cost of V? What number should you store for V in your map? How do you calculate it? This is the crux of the problem. Yeah.
It would be the cost to get to the destination from the next city plus the total of that city.
Well, the problem is, you say the cost of, all right, so you're looking at the cost of getting, let's say, to the destination from that city right there. Okay? In fact, let's call this V1, this one V2, and V3. So we know that the cost of getting to the destination from V1 is cost of V1. This one, the cost of getting from V2 to the destination is cost of V2. Cost of that one is V3, okay? So suppose you could look up cost of V1, cost of V2, and cost of V3. And let's say that, so then what's going to be the cost of getting from V to the destination?
It'd be the minimum of like the cost of V1 plus total V1.
Okay. So let's say the toll for this one is T1, the toll for this one is T2. The toll for that one is T3. So the cost of getting from this city to the destination is going to be the minimum of those three things, right? You've got to go to one of those three cities next. And so if you decide to go to V1, you're going to pay the toll to get into V1 plus whatever it costs to get from V1 to the destination. Same thing if you go to V2. You've got to pay its toll plus the cost of getting from there to V2. And same thing for V3. You just look up the cost, look up the tolls, add them together, find the minimum. That's the cost for V. Eventually, so if you compute all the costs, then you've sort of solved a general problem. You've solved it for every vertex, in particular for the start vertex. Okay? Can you see anything that could go wrong with this? Yeah?
What's the best way to handle like self edges?
Well, you mean a edge to itself?
Yeah.
Well, in a DAG, you can't have an edge to yourself. That's a loop. No loops in DAGs.
So if you have like Easton to Easton, is that 0 or is that
Okay. The cost of going from Easton to Easton is 0.
Yeah. So
Yeah, because you're already there. You're not following any. The path from Easton to Easton is a path of link is 0. There are no edges involved.
So you don't add that as a self edge. You just handle that case
Right.
manually.
Right. The three cases I showed you are all you need. Every vertex is either the destination, or it's a sink, or it's not neither of the above. Okay? So let me ask you this question. All right, suppose you start iterating through the vertices, and you go to the first vertex, vertex 1, it's the destination, so you set its cost to 0. Vertex 2 is a sink, so you set its cost to infinity. Vertex 3 is a sink, you make it infinity. And then you get to vertex 4, and it's neither of the above, and it depends on vertex 7 and vertex 8 and vertex 22. You go to look up the cost of those three vertices, and they haven't been computed yet. Now, some of you have been tempted to make instead of looking it up, to make a recursive call to compute it. Don't do that. What's the answer? How do you make sure that when you go to compute the cost of V here, you're guaranteed that all the costs you need have already been computed? Yeah.
Just go down the topological sort and make sure you check the distance for all of them.
Right. You do it in topological order, or reverse topological order in this case. So if we sort this in topological order, so I'll call this A, B, C, D, E, F, G. What's a reverse topological sort for this? From sources to sinks. I'm sorry, from sinks back to sources. What would be the first one in a reverse sort? G. So that's a sink. Then what would come next? Yeah, E. Yep, in this case we'd have to have F next. Then I just want things that, just working backwards, you'd have to have D. And then you could have either C or B. Let's say we do C, and then B, and then A. That's a reverse topological sort. So you do a reverse topological sort, and then look what happens. G comes first. Let's say you're trying to find, again, well, let's just change it so that our start is B, and our destination is F. Okay? So let's just apply the algorithm. Okay, we go to G. What's its cost going to be? It's a sink, but not the destination. What's its cost? Infinity. We're in this case right here. Then we proceed to E. Okay? It's in the third case. So we look at it, we look at all the choices we have for leaving E and find the cheapest one. Well, there's only one choice. the toll is 1, what's the cost of getting into G? Or what, I'm sorry, the toll is 1, what's the cost of getting from G to the destination, which is F? We look it up. It's already been calculated for us. So we add 1 to infinity, we get infinity, and that's the cost for E. That's the cost for E. Okay, let's do F. Which case are we in? Remember, F is the destination.
First case.
We're in the first case, so what's its cost? 0. Okay, now we look at D. D, there's 2 options. We can go this way, that way. Okay, if we go this way, we're going to pay 4 plus, let's look up E here, infinity. That's one way. If we go the other way, we're going to pay the cost for getting into F, which is 3 plus 0. So, which do we choose? 3 plus 0 or 1 plus infinity? 3 plus 0. Good. Now we look at C. It has 2 choices. We can go via this choice right here, and then the cost is 6 plus 3, which is 9. Or we could follow this path here, and that is 3 to enter F plus 0, which is 3. So obviously we picked the 3. And we go to B. What happens there? Yeah, there's only one choice, so there's 6 to enter D, and then to get from D to the destination costs 3. We look it up again right here. So 6 plus 3 is 9. Now that happens to be our answer, because our start was B. And then what about A, if we wanted to keep going? So it's either going to be 2 plus the B, which is 11, or it's going to be 8 plus the C, which is also 11. So it looks like it's 11 if I didn't make a mistake there. Okay? No recursion necessary except in the depth first search. After I did the topological sort, it's just filling in a table. And the purpose of the sort is to make it so you can fill in the table without, ever encountering an answer to a question that you haven't answered yet. That's the whole idea behind DAG algorithms and why you do a topological sort. And yet, I'll give a midterm. And I'll ask you to describe an algorithm on DAGs by sort of coming up with this sort of derivation. And people will write recursions. There's a question like this on the next assignment. People will come up with recursions. Don't do it. DAG algorithm, just think topological sort, figure out which direction you want to go. Come up with a non-recursive algorithm like that just to fill in the answers. Use the sort to fill them in the right order. All right, I've basically done the caddis problem for you here. Yeah?
You say figure out which direction you want to go, you can either in reverse topology.
Yeah, either in topological order or reverse topological order. Now, I could equally well have described the solution of this problem, but instead of computing, the first thing I decided was to compute the cost for every vertex, the cost of getting from it to the destination. Now, I could have said, for every vertex, let's compute the cost of getting from the source to it. Okay? If I did that, I would want to be working in the opposite direction. I go in topological order, and those equations over there would look different. And we'd be looking back at predecessors instead of forward at successors. Yeah?
So then would you store this cost? Would you store this cost or recalculate it?
Okay, so he's asking, do we store these costs as we calculate them, or do we recalculate them every time we need? Absolutely, you store them. If you recalculate them every time you need them, if we've got a diabolical graph, like I showed you last time, you can end up taking exponential time you end up recalculating some of these vertices an exponential number of times, and you just run out of time. So just create a hash map called cost, fill it in. This is meant to represent a hash map. Recalculating the cost each time you need it, like in our last step, I guess we looked up the cost of D several times. You're wasting time. Just make sure you calculate it and save it, and then just look it up. That's what makes it fast. only recursion should be the one in explore when you're doing the sort. Any other questions? Okay. Okay, I'm going to take a brief digression from graphs. This is a topic I've been meaning to talk about and just hasn't fit in up to now. And that is, I want to prove that any sorting algorithm that is comparison-based is going to take at least n log n time in the worst case. There's going to be some case that requires at least n log n time. In other words, so what I'm going to prove is that the sorting problem is omega of n log n. You cannot find a comparison-based sorting algorithm that is better than n log n in the worst case. So what I'm doing is I'm showing that the comparison-based sorting problem is n log n. So what are some examples of comparison-based sorting algorithms? Yeah.
Merge sort.
Merge sort, quick sort, insertion sort, selection sort, probably every sort you've ever studied, unless you've studied radix sort. Radix sort's not comparison-based. But general purpose algorithms where all they assume about the elements are that they can be exchanged, they can be moved around basically, or they can be compared. But they can't be taken apart and have their bits examined. That is a comparison-based sorting algorithm. And we'll show that no algorithm can do better than n log n in the worst case. Now, there's a simpler result I've talked about before. Suppose you have a comparison-based sorting algorithm. Could you have one that did better than linear? What's the proof that no sorting algorithm that exists today or is yet to be discovered can go faster than linear time? Yeah.
You'd have to look at each element at least once to determine that it's sorted.
Yeah. You've got to at least look at every element. You could take any sorting algorithm you want, and first thing you could do is check to see if it's already sorted and then stop if it is. That would give it a best case of linear, no matter how bad the worst case is. But you still got to look at every element. Okay? Now we're talking here about sequential algorithms. If you use multi-threading and parallel sorts, you can do better. But we're talking about just single-threaded programs. The technique, so that's easy to prove. It's harder to prove the n log n bound. And we're going to do that with using a technique known as a decision tree. So let me show you what a decision tree is. We're going to analyze insertion sort, and we're going to analyze what insertion sort might do, all the things that insertion sort might do if you gave it an array ABC. Now ABC stands for arbitrary integers, so there's 6 possible ways to sort. In general, there are going to be n factorial ways to sort n things, that many ways to permute. And all 6 are shown in that white box there. So starting, if the initial array is ABC, depending on what's bigger than what, we could end up with any of those 6 possibilities. So at this point, when we first start the insertion sort algorithm, that's all the algorithm could tell you at that point. Not that it would. Not that it's even thinking this way. But if we're taking a bird's eye view of the algorithm, we know that those possibilities are all on the table right now. And I've highlighted in blue the actual array that insertion sort sees at that point. Now, what's the first question? What's the first comparison that insertion sort's going to make? Remember, it's looking at that blue array right there. Yeah.
The integer at index 0 and the integer at index 1.
Say it again.
Like the first two.
All right, it's going to compare the first 2.
Yeah.
Yeah, so it's going to compare A and B. Those are the first 2. It's going to look, see if B is smaller than A, it's going to move B past A. So so that I just put in there the first comparison that insertion sort's going to do. Now, suppose the answer is no. Suppose B is not less than A. Which of those permutations have just been ruled out? Which of those permutations can not possibly be the answer when we're all done?
The third one and the fourth one.
Okay, the third one has B before A, so that's not going to work. Which was the other one?
The fourth.
fourth one, and also the sixth one. All three have B before A. So none of those can be the ultimate outcome. And again, insertion sort isn't thinking like this. We're sort of imposing what we know. Once you know that B is less than A, we know we can rule out those three things. So here we are. We're at this state right now. Insertion sort is still looking at that blue thing, but now we know there are only three possible outcomes. So given that B was not less than A, what is the next comparison that insertion sort's going to do? It's going to compare C to B and try to move C past B. Because A and B are already in order, it knows that. It's just trying to put C in the right spot. Now suppose it does that comparison and the answer is no still. So at this point we know that B is not less than A and C is not less than B. So which of those three options are ruled out at this point if C is not less than B? Second and the third. And in fact at that point, insertion sort would stop. If insertion sort did those two comparisons, it would stop and say, okay, the array is sorted now. And it sorted the array in two comparisons. So what you're going to see is that every leaf, any path from the root to the leaf is going to go through a series of comparisons. And that's, in this case, it shows you the comparisons that insertion sort will do when given a three-element array when the first two comparisons it makes come back false. It'll do those two comparisons and stop, and the array will be in that order. So the decision tree just shows you an exhaustive enumeration of all the possible comparisons that could happen. And what happens depending on the answer being no or yes. So back to here. The array is one of these three possibilities. Insertion sort's looking at A, B, C. We just looked at what happens when the answer is no. What happens when the answer is yes? So what if C is less than B? What's ruled out at that point? Anything that has C after B, and so that's A, B, C. So we're just left with the two possibilities here. And the array, why have I highlighted the array A, C, B in blue? Yeah, well, but why don't we highlight C? Well, that is the array that, the answer is that's the array that insertion sort has right now. It was working on ACB. When it found out that C was less than B, it swapped C and B, and now we have ACB. That's how insertion sort works. So now what comparison will, now that we're at this point of insertion sort, what comparison does it do next? It's going to compare C to A. So it just moved the C past the B, now it's going to try to move the C to the left of A. So it'll ask, is C less than A? Now what if the answer is no? C is not less than A. What are we left with? And if the answer is yes, we're at that situation. So in either of these cases, it took three comparisons. Insertion sort had to do three comparisons to get to those permutations. So we could continue this process, but I'll just show you the final, oops, there's the final tree. That is the decision tree for insertion sort when given a three-element array. Those are all the possible sequences and comparisons you can go through. And which one, any given run of insertion sort is going to follow one branch of this tree from root to leaf. And which one it follows depends on how the initial elements compare with each other. All right, so we're going to reason about this tree, or about trees in general, but I don't see if there are any questions about how you can construct them. Clearly, you have to thoroughly understand the algorithm to construct the tree. You've got to be able to figure out what sequence of comparisons it goes through. And it's hard enough to do it for 3 elements. You've got to keep a few things in your head. Doing it for 100 elements would be, of course, a disaster, but in theory, we can talk about the decision tree for 100 elements without actually building it. All right? So say I ask you to create a decision tree for selection sort for 3 elements. Could you do it? Even if you couldn't do it, you don't even have to be able to construct a decision tree. Maybe the details are just too overwhelming. You need to know what a decision tree is. So let's talk about decision trees. What would the decision tree for insertion sort with 100 elements look like? What kind of shape would it have? First of all, how many leaves would it have at the bottom? How many possible outcomes are there? 100 factorial. So it would be a tree with 100 factorial leaves. Okay, it's a big tree. Now, how long would the paths be? This thing has some paths of length 2 and some paths of length 3. What would the shortest path be in the decision tree for insertion sort? That's a veiled way of asking a different question. What's the different question you can answer to get that? What's the best case for insertion sort? In the best case for insertion sort, when given 100 elements, how many comparisons will it do? 99. It's linear time. So if the array is already sorted, it's going to do 99 comparisons and stop. So the shortest branch in this 100, this n equals 100 decision tree for insertion sort with n factorial leaves, one of the paths anyway is going to be 99 comparisons. Are all the branches that 99? No. What's the longest one going to be? There I'm asking for the worst case. Yeah, it's like 99 plus 100. Yeah, it's either 100 squared or a half 100 squared. I'm not thinking of my feet very well, but it's very long. It's way long. It's 10,000 or 5,000 or something. So it's a very unbalanced tree. But it has n factorial leaves. It's very unbalanced. Some shorter, some long. Okay. Now, suppose we did the same exercise for selection sort. What would its tree look like?
Balance.
It would be balanced because selection sort does exactly the same amount of work in every case. Okay? Every branch would have exactly the same length because it just stubbornly, it just does the same number of comparisons no matter how the initial array is organized. How many leaves would it have? That's a tricky question. At least how many leaves would it have? And actually, I should have said at least how many will insertion sort have. Well, I mean, what's the bottom line? If you've got every leaf is a permutation of the input array, there've got to be at least n factorial leaves, right? But in fact, for selection sort, there are more than n factorial leaves, or a lot more, because there are multiple paths lead to the same answer. Okay, so there are more than n factorial leaves. What about merge sort? What would its tree look like? Selection sort would be nicely balanced, but tons and tons of leaves. What about merge sort? What would you speculate? Yeah?
Fairly balanced.
Fairly balanced. The branches would be shorter than a selection sort because it's faster. And at least n factorial leaves. Quick sort, what would it look like?
Very unbalanced.
That's be an unbalanced one because you got the n squared worst case. Some of the branches would be really long. Some of them would be short. So every algorithm has a characteristic decision tree. Now, somewhere out there, maybe it's been discovered, maybe it hasn't, is the world's best sorting algorithm. The fastest sorting algorithm. Does the fewest comparisons possible. What's the best we can hope for its tree? Yeah.
All of its branches are like that.
Well, I don't know that that's too much to hope for, it turns out. So I'm going to weaken it. Instead of saying every branch is length n, we're going to say every branch is the same length. We're trying to minimize the worst case. I guess I should say that. We're trying to find my definition of the world's best sorting algorithm is I want to make the worst case as fast as possible. Okay? So to make to minimize the worst case, and otherwise to minimize the length of the branches, we need to make the tree as balanced as possible. If it gets unbalanced, then the worst case is too big. How many leaves will it have? It has to have at least n factorial, right? So let's just say it has no more than n factorial leaves. So in other words, the ideal sorting algorithm in terms of minimizing the worst case would have exactly n factorial leaves and be perfectly balanced. Because a perfectly balanced tree with n factorial leaves is the depth of that tree is the smallest you can have if you have n factorial leaves. And for a given number of leaves, if you want to minimize the depth of the tree, you make the tree perfectly balanced. So we have n factorial leaves perfectly balanced. That would be the shape of the decision tree for the algorithm with the best worst case. Well, how deep would that tree be? What would be the length of the branches, this perfectly balanced tree with n factorial leaves? If you have a binary tree with n leaves, perfectly balanced, what's its depth? Yeah, log of number of leaves, give or take 1. So the depth of this tree we just postulated with n factorial leaves, perfectly balanced, is log of n factorial. So we're saying that the best we can hope for a worst case is on the order of log of n factorial with comparison sorting a tree with n leaves. So we'll look at what log of n factorial is in a second. Basically, what I've just taken you through is all that stuff. I'm not going to read through it again. You can look at it later. But it gives us to this log of n factorial result. So we're just, all we did was we see what a decision tree is. We know every algorithm has one, whether we can draw it or not. They get pretty big. But the world's best algorithm is going to have n factorial leaves exactly, and it's going to be, at least it's the most we can hope for, n factorial leaves, no more. Perfectly balanced, which means its depth is log of n factorial, which puts the bound on the worst case. So theta of log of n factorial would be the worst case performance of this hypothetical algorithm. We can't do better than that. So before we go and try to pick apart log of n factorial, are there any questions I could answer about this? Okay. Okay, let's figure out what log of n factorial is. That's a weird looking thing. Well, log of n factorial is just log of the product of 1 through n. Okay? How can I modify that using the rule of logs? What's the log of a product? Sum of the logs. So it's that. It's just log of 1 plus log of 2 up to log of n, the sum of all that. And that is, certainly you would agree, that's less than or equal to log n added to itself n times. What's the argument for that? Who could justify that step for me? Yeah.
Log of n is greater than log of n less than.
Yeah. Log of n is bigger than log of 1. Log of n is bigger than log of 2. Every one of these is bigger than one above, except there's a tie right here. So add them up. Yeah, it's got to be less than or equal to that sum, even if n is 1. Okay. Well, what's that we have? What's that sum? What's another way to write the sum without the dot, dot, dot? N log n. So remember, log of n factorial was the order of n, roughly n factorial, log of n factorial was number of comparisons in the worst case for the world's best algorithm. So it's bounded above that sum is no bigger than n log n. Well, we got to put a bound from below as well. We can also say that it's bounded below by something like n log n. We'll know what it is. Well, let's try that. Let's look at it a different way. Here's log of n factorial. It's that. This might be slightly harder to see. So here I am replacing this sum. I'm saying this sum is greater than or equal to this sum. And there are n over 2 terms in this sum. What's the argument for that? There's twice as many terms in that sum as in that one. So how do we know that this one is greater than or equal to that one? Yeah?
That is the middle one in that one, so everything in the second half is big.
Right. So basically, I'm saying, okay, forget about the first half of this sum. That gives us some value. Just look at the last half of the sum. Okay, n over 2 will match with n over 2. It's greater than or equal. Then the next one is n over 2. It's going to be smaller than its corresponding value, and so on. So let's say this is log of 1 up through log of 10. This is going to be like log of 5 up through log of 10. I'm sorry. It's going to be log of 5 plus log of 5 plus log of 5. Match them up. Clearly, this one is bigger. Add these up. It's going to be less than the sum of the first half, the last half of that sum right there. Right? So what is log of n? What is that sum? That's another way to write it. To get rid of the dot, dot, dot.
N over 2 log of 2.
Right. N over 2, log n over 2. Using, the log of a quotient is a difference. So it's n divided by 2 log n minus n over 2 log 2. That n over 2 log 2 is a low order term. Throw it away. This divided by 2 is a low order term. Throw it away. So that gives us a lower bound. The first one gives us the upper bound. It's O of n log n. This shows it's a low. It's also the lower bound is also theta of n log n. So the whole thing is n log n. We've squeezed it between two things. So notice this one we definitely showed. This was definitely n log n was bigger than log of n factorial. Here we're making a big O argument because we had to get rid of lower terms and leading constants. But the upper bound is on the order of n log n, the lower bound is on the order of n log n, so the thing is n log n. So bottom line, log of n factorial is theta of n log n. And that completes that argument that no matter how clever you are, you will not find a comparison-based sorting algorithm that has a worst case faster than n log n. This gives you a taste of what algorithms researchers do. One thing they'll do is solve some problem, and the next person will come along and solve it better. And then someone else will publish a paper improving that. So they'll keep getting the algorithm better and better. And eventually, someone will say, to heck with this, and will be looking for a faster way to do it and think there isn't, and then prove they've reached the lower bound. Some proof will come along saying you can't do better than what we've already seen. And it's a lot easier, it's typically easier to come up with algorithms than it is to prove some result that applies to all possible algorithms for a problem, like we did here. Okay, any last questions about that? All right, let's take a short break and we will move on to something different. Okay, we're continue talking about directed graphs, and the next algorithm we'll talk about is a strongly connected component algorithm. So let me begin by saying what a strongly connected component is. So we're going to say that two vertices of a directed graph are connected if there's a path from one to the other. Or, I'm sorry, if there's a path from one to the other and vice versa. So what would be a pair of connected vertices? What's a pair of vertices where there's a path from one to the other and back? B and E, for example. What about G and L? Yeah, you can get from G to L and L to G. So the largest possible chunks of a directed graph, where every pair of vertices in the chunk are connected to each other, that's called a strongly connected component. So I wanted to, the algorithm we're going to look at is going to divide this graph, or divide a graph in general, a directed graph, into as few chunks as possible, where each chunk is strongly connected, meaning every pair of vertices, every vertex is reachable from every other vertex. So what's the fewest number of chunks you could divide this graph into that have that property? Look at D, for example. D is going to be part of some chunk. Can any other vertex be part of the chunk D is in? No, because D is a single. Okay, so D is a chunk to itself. Right? What's another thing that is in a chunk to itself? A. All right. You can reach everything from A, but nothing can reach A. Sort of the opposite of D. Well, actually, I just told a lie. No, I didn't. Okay, A is in a chunk to itself. Okay? What's another chunk? We want the largest possible chunk. We could just say every vertex is a chunk to itself, but I want the largest possible chunks. Yeah. Okay? Say again.
G to L.
Okay, so that bottom area, G, H, K, L, J, I, all of them together form a large chunk. And you'll notice there's a way every pair of vertices is connected because you can cycle through G, H, K, L, J, I, G. So that's a chunk. What's another chunk? BE is a chunk, and CF. So it turns out that's the fewest chunks we can make. So for any directed graph, you can decompose it into its strongly connected components. Now, if you take the strongly connected components and, so I've got dotted lines around them, think of those, what we're going to do is define a new graph called the metagraph. So to do the metagraph, what we do is first remove the internal structure, and if there are any duplicate edges between vertices in this simplified view, we eliminate them. So are there any redundant edges in this metagraph here? Right, there are two from BE to CF. You normally wouldn't see that, so we'll get rid of them, just leave one. So what is left is called the metagraph. So this is the metagraph of the original graph. It contains 5 metavertices, each one corresponding to a chunk in the algorithm, in the strong connected components. Each is a strong connected component of the original graph. And we'll call the edges meta edges. And we'll label them with the, all the labels from the original graph. Right? So a strongly connected component produces this. Now, turns out that the metagraph is always a DAG. So notice that is a DAG, no cycles. Why does it always have to be a DAG? Why does the metagraph have to be a DAG? Mm-hmm.
So if they were connected to each other, they would be the same chunk. They would be the same chunk.
Say it again louder.
If they were connected to each other, they would be the same chunk.
Right. For example, if there are a way, if you could get from B to E and then back to C to F, in other words, if there was a cycle in this metagraph, that would imply that those two metavertices should have been in the same chunk. So we didn't do the original decomposition correctly. So the metagraph will always be acyclic. It's a DAG. And the reason we're interested in strongly connected component algorithms is the following. Sometimes there are algorithms you want to apply to directed graphs. And it's the way to do it is to first create the metagraph, solve the problem for the each of the vertices of the metagraph, and then apply a DAG algorithm to solve the overall problem. So we'll see some examples of that. But it's just sometimes it's simpler to think about DAGs. DAG algorithms, we know how to solve them. We do a topological sort and do something. If we can arrange to make the algorithm so that we solve the problem for the chunks and then solve the DAG problem, we can sometimes come up with pretty effective algorithms. Okay, so we're going to play around with DAGs. We're going to start by looking at some problems where we're going to look at strong net components. We're going to look at some examples where we use them in algorithms. We use an algorithm for this, and then we're going to look at how the algorithms work. So first of all, can I answer any questions about what I mean by strong connected components? Yeah?
Do the labels reflect the original structure?
Yeah, the labels don't have to, but I've left the labels there so you know that this chunk at the bottom consisted of those vertices from the original graph. Makes it easier to go back and forth. Just as an exercise, let's go back. Suppose you wanted to add some edges and reduce this thing to a single chunk. What's the fewest edges you could add to this thing and end up with a single strong connect component when you did the algorithm?
5.
Yeah, I got a 5. Can anyone do better than 5?
2.
2. That's better than 5. Can anyone do 1? No takers? Okay, which 2 do we add? So if we add an edge from this sink back to the source, and from this sink back to the source, would that do it? Yeah. Turns out it would in that case, because anywhere in that upper, except for D, anywhere else in that upper part of the graph, you can filter down to here, and then if you get a way to go back, you're good, and do the same thing for D. What about if I added an edge from down here to A, and then add an edge from D over to E? Would that do it? Yeah, it'd be a little more convoluted, but it would still do it. Sometimes it takes some cleverness to look at the minimum number of edges. Okay. Let me ask you a question here. All right, so there's a city that only has one-way streets. So you could model the traffic grid as a directed graph. So the vertices would be intersections. The edges would be street segments connecting the intersections. The mayor claims that every intersection can be reached from every other intersection. That's a good property to have in the city. You can get anywhere from anywhere. What's an efficient way to test this claim? Yeah?
Create a metagraph, and then if it has more than one vertice, then it's
Okay.
untrue.
Right. So the answer is you find the strong connected components, and if the mayor's claim is true, the entire city will reduce to a single connected component. You can get to every vertex, and every other vertex, there'll be a single strong connected component. So that's exactly how you would do it. Now suppose that's not the case. So the mayor backs off on his claim and says, okay, if you start driving from City Hall, you will always be able to get back. Okay? So he's saying, okay, maybe you can't get anywhere from anywhere, but at least if you're at City Hall, you can, anywhere you go from City Hall, you can get back where you came from. Or you can get back from where you went. So how could we use a strongly connected component algorithm to answer that question? Yeah.
See if there's any exits from the strongly connected components in Hall of it.
Okay, as you said, see if there are any exits from the strong intent component that City Hall is in. Okay? What's another way of saying, seeing if there are any exits? What's a vertex with no exits called? A sink. So you would run the algorithm and make sure that City Hall is in a sink meta-vertex. So you compute the metagraph, see which meta-vertex City Hall is originally part of, and make sure it's a sink. If it's a sink in the metagraph, then there's no way to escape. You can reach everything in that metagraph, in that vertex. So there's a couple simple questions. So let's look at a slightly more complicated one. You may not remember the price-cost problem, but I'll remind you what it was shortly. We did it for DAGs. I want to do it on an arbitrary directed graph. So let me bring back up this one here. Okay. The problem was this is actually pretty similar to the Caddis problem. Every vertex has a price, which is labeled in white. So the price of A is 8, and the price of B is 4, and the price of E is 1. And every vertex has a cost that you have to compute. And the cost is the highest price of a vertex reachable from you. So I've already pre-computed the yellow costs. Why is the cost of F2 here, this yellow 2? Given that definition right there. F is a sink. Why is the cost of a sink the same as its price? Yeah.
Because it can't reach anywhere else.
Right, there's nothing reachable from it except itself. So its cost has to be its price. Now, what about this case here? Let's look at the this one here, B. Why is its price is 4? Why is its cost 6? Yeah.
So it can reach a vertex that has a cost of 6.
Well, okay, I'll put it another way. You can reach. The definition says it can reach a vertex that has a price of 6. Okay. So from B you can get to E, which has a price of 1, and to C, which has a price of 6, and so on. The highest price you can reach is 6, so its cost is 6. But there's an efficient way. What's the efficient way to compute all those yellow things? In reverse topological order. So if you start with F, it gets a 2. And then to compute G, so to compute B, my point is to compute B's yellow 6, you don't have to look at everything that's reachable from it. You just have to look at its direct neighbors. If you've already computed that yellow 6 for E, then without looking at C and F and G, you know that none of them have a price higher than 6. And so to compute B, you just have to look at B's price and all its neighbors' costs. And similarly for D. To get that 6 right there, you look at its 2, you look at the white 2 for D, and you look at the cost of B and the cost of E, and you take the largest, and you get the 6 right there. So you do it in reverse topological order and fill it out. Very similar to what we talked about at the beginning of class today. Okay? So yeah.
How come A has 8 and not 6, since you can only reach D and B?
Okay? The question is, why does A have a yellow 8? And the answer is, the cost is the highest price reachable from you, including you itself. So A has a price of 8. And so that's where that 8 comes from. So for every vertex, for a sink, the price is the same as the cost. For every other vertex, you look at the cost of the neighbors and the price of yourself and take the largest. And if you work backwards, you can just fill in the table without having to do any recursion. So that's the DAG algorithm for the cost of a vertex. Any other questions I could answer here? Okay. Now, what happens if we start make this not a DAG? What if we started adding arrows and make this not a DAG? Then our DAG algorithm doesn't fly anymore, right? We can't topologically sort it. So, let's see if we can solve this problem on a DAG by using strong net component algorithm. So back to it. I want to go up to here and go forward a little bit. There we are. And let me try to make a copy of it. Sure, I got white here. Okay. So let's do an experiment. What if we had to solve that price cost problem on this graph right here? So for a minute, ignore the dotted lines. Just look at the original graph. So we can't use the DAG algorithm, but how could we use a strong net component algorithm to make it so we could use a DAG algorithm? Yeah.
Well, since everything in a strongly connected component is reachable, then you find the highest cost in each component, and then you can do a topological sort with your components, and then do the cost price thing that we did previously.
Okay. That's it in a nutshell. Let me write some prices in here. 1, 2, 5, 3, 4, 6. And then I'll go up here and write like a 1 and an 8, 5 and a 4, a 9 and a 10. So forget about the algorithms for a minute. What is the cost of G? Okay, is the cost of G2. Remember, what's the definition of cost say? It's the highest price reachable from G, including G itself. So what is the cost of G? It's not going to be 2. It's 6. Okay, because the only thing you can reach are the things in that clump. Okay? So that's good. What is the cost of B going to be? It's going to be 9, because you can reach that D with a cost of, that has a price of 9. What about the cost of C? Turns out it's 8, because you can reach F and C, but that's just 8 and 1, and plus you can reach the things in that lower clump. And the largest one down there is 6. What if I change this slightly? Let's make this a 2. What is the cost of C? 6. Now I'm going to suggest something. This is what when she answered my original question, what she was getting at. Suppose we replace, so we got this, suppose we ran our strong component algorithm, we're looking at this. I'm going to associate with each clump independently the largest, I want to run our DAG algorithm for computing costs on this graph, on the DAG, on the meta graph. That means I've got to associate a price with each meta vertex. Now, I claim that in the original graph, the cost of any vertex, the cost of any 2 vertices that are in the same clump is going to be the same. Okay? Do you buy that? Why should the cost of B and E be the same? Simply because they're in the same clump. What's the argument for that? Yeah?
Because they have access to all the same nodes.
Right. They have the set of vertices you can reach from B are the same, or you can read. The set of vertices that have a path from D are the same ones that have a path from E. Okay, you reach the same vertices from B as from D. The same thing goes from C to F. So what I'm going to do is associate with each clump a meta price, if you will. And that meta price is going to be the largest price that occurs in that clump. So what should the meta price of this bottom thing be? What should be the meta price right here? 6. And what's the meta price of this going to be? 2, because the largest of C and F is 2. Over here, the meta price is going to be 5. The meta price of this will be 10. The meta price of this will be 9. Okay? Now I'm going to compute the meta costs running my DAG algorithm. So working backwards, starting from the sinks in the metagraph now, back to the sources, what is the, looking at this bottom chunk, what is its meta cost? Meta price is 6. What's its meta cost? Yeah, also 6. It's a sink. Now, what about this guy up here? That'd be sort of next, or you could do it next. What's its meta cost? Yeah, and the thing, remember, now we're working on the metagraph, so we would look at this thing here, the CF chunk, as a price of 2, but we can reach something with a cost of 6. We take the larger of those, and so our meta cost is 6. Okay, what would go with D here? That's 9. What would go up here with this chunk? Let's see, that we've got a price of 5, a meta price of 5. You can reach a chunk with a meta price of 6, and one with a meta cost of 6 and a meta cost of 9. The largest is 9. So you get a 9 right here. And then what about up here for the A? That's going to be a 10. So let's review what we had to do to solve the problem. We took the original graph, turned it into and created the metagraph. We associate with each meta vertex a price. And how do we obtain that price? Yeah.
The highest cost net vertices.
Right. The highest price of anything that occurred in that chunk. So the highest price of the vertices in this meta vertex was 6, and so that becomes the meta price. So we did that. Now we have an instance, a DAG instance of our original price cost problem. It's just that the graph we're working with is the metagraph. I know it's confusing to look at the scroll here and see it, but it's just 5 vertices, each with a price. So we compute their costs, just like we would for any DAG. And that's what ended up in the 6s. Keep in mind, when you're running that algorithm, the algorithm doesn't see this internal structure. It just sees vertex, price of 6, vertex, price of 2. And the only edges it sees are this one and this one of these, this one and this one. So we run the DAG algorithm and we compute the costs. What's the last step we have to do? Because we wanted to, the original problem was to associate costs with each vertex in the original graph. We've computed costs for each vertex in the metagraph. So what's the answer to the original problem? How do we figure out the cost of G in the original graph?
Cost of this chunk.
Cost of this chunk. So this 6, which was the cost of this meta vertex, is also going to be the cost of each original vertex. Same thing goes for every chunk. So that's why you use strong component algorithm. Is it can be hard to see how to solve a problem on a general directed graph, but sometimes you can solve the problem on the metagraph, which is a DAG. But to do it, you've got to find a way to create the instance of you can create the metagraph. You've got to add data to it, like we did by figuring out the prices to work with. And then you've got to translate back after you solve the problem in the metagraph. You've got to convert the 6, in this case, into the cost for each of these. So I'm not saying it's easy. You have to know that you can solve the original problem on the DAG, and you got to have some way of going back and forth between the graph and the metagraph. But that's the reason we have this, reason we study this algorithm. Any questions I could answer on that before I move on? And this doesn't always work. Sometimes you just have to solve the problem without resorting to strong intent components. But when it does work, it works nicely. Okay. We already looked at that. There's our SCC. We looked at these algorithmic challenges. All right, so I'm gonna make some. I got 5 minutes left, so I'm just gonna build up to make a few observations that'll help us next time. If we start explore at a vertex that belongs in a sink in the metagraph, it will visit all the vertices in that sink and then stop. So that's the first observation. So we know the answer. We know that this bottom thing is going to be a sink in the metagraph. So is it true that if we start exploring at a vertex in that bottom chunk, so G, H, J, K, L, or I, and we explore, it will visit every vertex in that sink and then stop? You buy that? Let's try it out. Let's start with G. So we'll just do an explorer. So we go to H, that takes us to K, to L, to J, to I, then it starts backing out. So we have, if we had some way of knowing that a vertex belongs to a meta-sink, we could find all the other vertices in that meta-sink. But that leaves two problems. The first problem is, how do we find a vertex that we know is in a meta-sink? And the second problem is, after we've found a meta-sink, how do we find the rest of the chunks? So our algorithm is going to be like this. We're going to sort of peel off, we're going to, by cleverly exploring the right thing, we're going to find the chunks. By starting with the meta-sinks and working back to the meta-sources. But we got to find a solution to these problems right here. Right? We're going to exploit this property. If x and x prime are strong intent components, and there's a path from a vertex in x to a vertex in x prime, then the highest post time in x is bigger than the highest post time in x prime. So let me just show you with an example. Let's start with C and explore. So that's 1. F will get the 2, 3, 4, 5, 6, 7, 8. Okay, so we just did that explore. So my idea is, let's see, let x be C. No, strong intent component. So this right here is x. This right here is x prime. Is there a path from this thing to this thing in the metagraph? Yes. So what I'm saying is that there will be one of these vertices in the meta vertex will have a higher post time than all the post times down here. So you see here, C and F both have higher post times than appear down here. And that's always going to be the case. Let's try it again. Let's start at D. Well, that's kind of vacuously true. Start from A. Now, look at every vertex is in some chunk. So let's take that chunk BE. The highest post time in BE is bigger than the highest post time in CF, which is higher than the highest post time in that big chunk at the bottom. And the post time for A is bigger than anything else in any chunk. Okay. This is just summarizing what I just said. So it just always works out that way. And the reason is, if you visited C, and then you visit, you're going to end up in that chunk below, and that chunk below is going to get all its post times assigned before C gets its post time. And I'll stop at this observation. The highest post time, if you do a depth first search on a directed graph, the highest post time is going to belong to a vertex in a meta source. You can see it happen right there. There could be multiple vertices in a meta source. There could be multiple meta sources. But if we do a depth first search, we're going to guarantee we can identify a vertex that occurs in a meta source. Okay? Yeah.
What if you, I mean, it worked out that way because of the, like, vertices we started at, but
Mhm.
is there a way to choose vertices to explore where that isn't the case? Or
Okay, it doesn't matter if you say you started with A, clearly it's going to get the highest one. But if you start somewhere else, you're going to finish with all those vertices. You can't have reached A because it's in a meta source. And so when you restart Explorer for A, it's going to get the highest one. Play around with it and you'll see, you're guaranteed. So what we've found is a way to always find a source. And find a vertex that's guaranteed to be in a meta source of the eventual metagraph. So we'll exploit that next time.
Thank you.